recorded and it will be published on our YouTube channel. Okay, and it might take 1 or 2 weeks before the video is available. However, we normally take it serious or high critical on our end. So if we do publish it before 1 week or 2 weeks, we will also notify you. Yeah. So back to you, Akanksha. It's a pleasure to have you and welcome back everyone to our user group.
Thank you so much, Sean, for introducing me. Let me start sharing my screen.
I'm pretty sure you do have access to share it, correct? If you don't, remind me and I'll be happy to grant it again.
Yeah, I think that is what I'm figuring out. It's asking me to quit and relaunch. Do you mind if I quickly drop and rejoin?
Sure, please
Yeah.
do that. Mhm. So the speaker is having a small technical issue. Thank you for your understanding. She will be right back. It seems like she's back. So you do have access to share your screen, correct? You are on mute though.
Sorry, somehow it's not allowing me. I Okay, let me join from browser. So sorry for the confusion. We
No,
have
it's
tested
okay.
it before. Somehow it stopped working.
No, that's fine. It's okay. That's part of our expectation. That's fine. Mhm. Now we can see it. That looks good. Perfect. Mhm.
Thank you. So, good morning, everyone, and good afternoon to everyone else joining from other side of the country. And thank you for joining me today. My name is Akanksha Mishra, and I'm a senior data engineer at Amazon. I have spent like last 7 years working and building large scale data pipelines in production here while working here in Amazon. And I'm here to basically give you details about what, like, based on my learning. And today we are going to talk about something which is really important in this modern AI world, which is silent failures in data system. So I'll start with the presentation. Hope you all can see the screen that I have shared. So uh, so today, this is a very important and interesting topic, which is silent failures in AI data system. These are the things which keeps production system up and night, but often in a ways that we don't realize yet. We are diving into silent failures in data systems, specifically looking at what I call risk drift and pipelines. And if you see the sheet, the subtitle here is really important. We are looking at failure modes that don't announce themselves. In traditional software engineering or in data engineering world, when something breaks, you know it. Your pipeline fails, your CI/CD pipeline returns an error, or and you get active page on if or for an all-gone engineer. Your phone buzzes at 2 a.m. or 3 a.m. in the night, you investigate, you fix it, and you deploy it. You deploy the issue, you deploy the changes, you're back to sleep, clear cause and clear effect. But in AI augmented systems, failures can be much more insidious. They degrade the quality and they degrade quietly. They compound over time, and by the time you notice them, the damage has already been done. Now, let's talk about this. Imagine waking up one morning to discover that your recommendation engine has been working fine, your dashboards are green, but your recommendation engine has been giving progressively worse recommendations for past 3 months. And you have been training new models on the output of your old data the whole time. And no alert fired, no exception thrown. This is a new reality of production AI systems, and it requires fundamentally different approach to system design and monitoring. So this the today's session, it is a technical deep dive, and but I promise we'll walk away with actionable patterns that you can actually apply in your own pipelines. And these aren't just theoretical concepts; these are the lessons that even I have learned, including my pipeline, which I debugged at 3 a.m. in the morning. So, just one quick note. I'll be taking questions at the end of the session. We will have ample amount of time at the end of my presentation. Just jot down all your questions and yeah, let's go. Let's deep dive and talk about why this even matters in the first place. So, moving ahead, I want you to look into this comparison, the comparison between the traditional system and the new AI augmented pipelines that we are dealing with in the real world now. On the left side, we have a traditional system. When they fail loudly. A service crashes, you know immediately. A database returns an error, it's in your logs. A build breaks, your CI/CD pipeline returns like turns red. This is what I call hard errors. They surface fast, they are traceable, and most importantly, recovery is deterministic. You fix a bug, you deploy, and you're back in business. But look at the right side of the slide. It's AI augmented pipelines. These fail differently. Output keeps flowing, your dashboard stays green, your SLAs are met, but underneath the surface, the quality is eroding. And here's the kicker, the degradation accumulates slowly. There is no explicit error signal raised. And but by the time you actually identify there's some kind of issue, or like we talked about the recommendation system, right, where the you started getting worse recommendation, the damage is already done. uh, Usually you get to know by wrong recommendation, or when the business metrics are impacted, or you actually get customer complaints, and it's often always too late. The contamination has already spread through your entire pipeline. And this is a fundamental shift we need to understand. AI failures are not binary, they are gradual, they are probabilistic, and traditional monitoring tools won't be able to catch them. So, what does it actually look like in practice? Let me walk you through our agenda for today. Here's all what we will cover. We'll discuss about silent failure patterns. We will discuss about chain pipelines. We will discuss about non-determinism and observability gaps. We will discuss about infrastructure and automation risk. And then we will discuss about design principle for resilience. In short, let me give you a brief details about all of them. So first, what exactly is a silent failure pattern? In silent failure pattern, I specifically want to focus on data drift and concept drift. I'll explain why your models keep producing outputs when they shouldn't be trusted anymore. Second, exactly is a chain pipeline risk? So most production AI systems aren't just one model, they are chain of multiple models, feature engineering steps, post processing, etc. etc. We'll see how probabilistic error compound over multiple stages, and this is what we exactly call the chain pipeline risk. Now, third one is basically non-determinism and observability gaps. Uh, how to explain this? So basically, you would have experienced it in your AI models that, and you cannot reproduce the same bug that you received last week or last night, right? Why does your model keep giving different outputs at the same time with the same inputs and everything Same, like features same, everything is same. And why is your monitoring dashboard is completely missing the semantic failures? We will discover all those in the non-determinism and observability gaps. Now, fourth one is basically infrastructure and automation risk. Mostly, we'll cover cost scaling surprises using in the new AI augmented pipelines, how the AI data, how the AI generated data is contaminated, and the dangers of over trusting automations. We will cover those topics in section 4. And finally is basically design principle for resilience. We'll talk about how to design like good pipelines, how to architect your pipeline from day one. And honestly, I'm here not to scare you all with the failure modes. I'm here to give you like the detailed instruction about what failure modes can be and how to actually avoid them or mitigate them by designing right architectural pipeline using metadata, trust boundaries, inhuman loops, and we'll cover all those in the later sections. So let me just start with the core problem for today. So I want you to really internalize this statement. The most dangerous failures in the AI system are not the ones that crash your pipelines. They are the ones that let it keep running while the quality of its output quietly erodes. Understand this statement. Think about what this means. In the traditional system, as we discussed, you get an exception and your execution stops. Bang, right? Everything stops. You get pages, you get tickets. You have to actively work on it to resolve the issue as soon as possible because it is actually impacting your pipeline, it is actually impacting your downstream customers. But you get back, you check the log, you actually know the stack trace, you know exactly where to look at by understanding the log, by deep diving in logs. You get monitoring alerts and the problem is visible and urgent. You actually solve it and basically will take some time, 1 day, 2 day, maybe few hours, and then your pipeline can be up and running. But what happens in AI system? In AI system, the errors aren't loud. They don't crash your pipeline. Instead, they quietly erode the quality while everything appears to be running fine. The degradation is gradual, the feedback is delayed, and by the time you notice it, the damage has compounded across your entire system. This is what we are up against in this today's world. This is a new failure mode that the traditional monitoring was never designed to catch. So let's break this down into specific failure patterns that I discussed in the last sheet. And let's start with the most common one, which is failure pattern number 1, data and concept drift. So these are the fundamental issues. Models are trained on snapshot of reality. You collect data, you train your model, you deploy it. But but reality does not stop moving, as we all know. It shifts. Models don't automatically know when to start trusting their own outputs. So let me distinguish between these two categories. What exactly is a data drift versus what exactly is a concept drift, right? So when we call data drift is basically when the statistical distribution of your input feature changes. If we take real world example, I will put it as imagine building a fraud detection model trained on transaction data between January to March. During this period, the average transaction costed around $40 to $45. Mostly purchased happened around 9 a.m. to 6 p.m. and 70% of the transactions are domestic. Clear, you have trained your model in this data. Now there's a shift, right? It's December, it's holiday period, your holiday shopping has started. Now the average transaction amounts have jumped from $40 to $45 to somewhere around $120 to $150. People started shopping for deals. International shipping has spiked by 40% of the transactions. Your model is seeing input pattern that it has never been trained on, right? It but this is the most dangerous part. It still confidently produces predictions. It does not flag uncertainty. It does not say that, hey, this looks different from what I was trained on. So from model perspective, it's doing its job. From user's perspective, those predictions are increasingly unreliable. You start seeing false positive, legitimate holiday purchases are flagged as fraud, or worse, you start more false negatives because the fraud patterns have shifted, right? So basically, overall predictions become unreliable. This is what we call as data drift, where the entire statistics of your input feature changes. Now, let's move what exactly is a concept drift. I would say concept drift is more subtle. This is when the underlying relationship between your input and output changes, even though the future distribution might exactly look the same. Now, here's an example. You learned. So let's discuss about. I would say let's discuss about an option where a user is on a website where they can go and upgrade to some premium package, and they just have to click on a button on the website. So your model is learned that the user who clicked on a premium upgrade button are likely to convert, right? But for 6 months, the relationship held perfectly fine. The click rate was the best predictor. Then your product team redesigned the UI and moved the button to the more prominent location. Now this actually caused drift because now the user started clicking on that button more out of curiosity rather than actually wanted to converting. This signals curiosity. This does not signal basically strong intent to basically convert. This is called a concept drift and it's incredibly hard to catch through traditional monitoring. Now, why does drift persist uh, in the modern world, right? Or even in the prior world as well. What exactly is a drift and why it actually persists undetected? Because standard infrastructure monitoring tracks throughput, latency, error rate, operational metrics that we all cover in our current pipelines that we will build in our day-to-day life. We do not track prediction quality. We do not track semantic correctness. Your dashboard will stay green while your model quietly produced garbage. Drift can persist for weeks or months before it surfaces in downstream outcomes. Your lower conversion rate, you get customer complaint, you get revenue loss, and by then you have weeks and months of bad production contaminating your pipelines. So drift brings us even to a bigger discussion problem, which is error compounding. And actually, let me show what exactly it means. So, this brings us to failure pattern number two, as I mentioned, error compounding in chain pipelines. So, now if you look at this diagram, uh, first we have initial accuracy, then error amplification, compounded output. Production systems are rarely a single model making single decision. They are orchestrated set of multiple AI models, feature engineering, model inference, post processing, downstream aggregation, etc. etc. Each stage consumes from the output of the previous one. Now, here's the critical insight: probabilistic error do not stay contained to the stage where they originate from, they amplify. Let me walk you through a concrete example from the recommendation system. This is a real pattern that I have seen in production. Now, imagine building a production recommendation system where stage one is basically understanding the users, right? And I will explain how the chain works in this example. The first model looks at the user browser, browsing history, and purchase history and creates a summary of what kind of product they like. Let's say they are interested in outdoor gear. The model has 2% error rate, meaning for every 2 out of 100 users, it gets preferences slightly wrong. Of course, not terrible, right? 2% is nothing. But when the same output of this model goes in an input to the next model, for example, the next model is finding similar products. The second model takes the user summary and finds similar products that match. But remember that 2% of those user summaries coming is already wrong. So the model is working with some bad information, plus it makes its own 2% mistakes in matching, which is roughly around 4% of production selections are off target. Now we are moving into further stage, which is stage 3. Let's take an example. We are ranking the products now. The third model takes those product matches and ranks them by predicted likelihood of purchase. It is receiving around 4% of corrupted data from the previous stage, plus adding its own 2 to 3% of error rate. You are now seeing somewhere around 6 to 7% of bad rankings. Now, stage 4 is basically, let's consider stage 4 is the final stage. We are personalizing the display. The final stage applies user specific rules, hiding products which are out of stock, checking user reason, hiding products which are not available in users actively where it stays in that region. But it's consuming around 6 to 7% of the bad data from the previous stages, and it's adding its own. So by the end of this, you might have 8 to 10% of the recommendation being completely garbage or wrong, I would say. And this compound further if the recommendation gets logged and used to train the next version of the model. And I'll just like to point this out. The math isn't just additive. It's sometimes the error cancels out in some of the stages, sometimes it multiply. By the principle holds, error accumulate and they amplify throughout the chain. And now here's the part, right, that makes especially hard to debug. So, for example, your customer complains that they got a terrible recommendation. Winter coats were suggested as recommendation in summer weather, right? Or mostly, for example, adult wear is actually shown to a teen account. You look at the output of the first stage, the final stage, the personalization layer. It looks fine. It has done like it is personalized display in a proper way. That is how it is supposed to work. Then you go back and you check the ranking model. It has done the ranking in a right way based on whatever input it has received. So you go back and understand finding similar product model, and then you still could not find any issue, and then you go back to stage number 1 and you actually identify that okay, this is the place from where the error originated from, right? But the drift has started like around 3 weeks ago, right? By the time you discover this, thousands of bad recommendations have already gone out, and some of them has been used for training data. This is why error in chain pipeline compound and amplify, and we should have proper mechanism like metadata and lineage information to track back from where the error originated from. Those are non-negotiable. You need to be able to trace backwards through the entire chain and understand why the confidence score at each stage has gone down and where the corruption originated. So I hope I was able to explain chain pipelines. So let's move into another tricky problem, which is reproducibility, or more accurately, I would say the complete absence of it. So this is a failure pattern number 4, which is called non-deterministic inference behavior. I think everyone working in AI data space would have had this experience. A user reports an error, you want to reproduce it, you have the same input, the same model, but you get different outputs every time. The bug does not show up. You close the ticket, you say that you cannot reproduce, or you ask your customer to get back if they again see this error. Sounds familiar to everyone? Now, this is a reproducibility problem in the AI system, and it is everywhere. Many production AI inference environment introduce sources of non-determinism. Language models have setting that intentionally add randomness to make outputs more creative. Some systems accidentally leave training mode features on during production. And when you run an AI model in the cloud across multiple servers, they might process each request in different orders each time. And the bottom line is feed the same input, your AI system will produce different results every time. The same input can give you meaningfully different results. It's not like one would be non like one would be wrong or the other would be better, but they will just produce different results every time. Now, what does actually it breaks? If you look at the right side of the screen, it actually breaks reproducibility, auditability, debugging, compliance, testing. Now, what exactly is reproducibility? You cannot uh, replay a pipeline that does not guarantee same result. And what it actually makes difficult, debugging. It is almost impossible to debug the error. What exactly I mean by auditability? You cannot reconstruct exactly what model decided and why. This is a serious problem if you are in a regulated industry like healthcare. They need like proper answers. Now, debugging. So, intermittent failures are nearly impossible to isolate. You cannot write tests that reliably fails. Going ahead, compliance. Compliance is the most important part. It's for regulated industry like finance, healthcare, and defense. They require explainability and traceability. Non-determinism makes it very difficult. Now, testing, which is the last step that I want to mention, your deterministic test suite break against non-deterministic output. How do you assert e- equality when the output changes every time? So overall, the five things that I have discussed, this is the architectural problem, not just a tuning problem of your model. You need to design your pipeline in a way that can help you with determinism from the start. So let's talk about particularly in dangerous feedback loop. So now this brings us to failure pattern number 4, which is AI generated data contamination. Now, this is one of the most underappreciated risk in the AI pipelines. It's a feedback loop that can destroy model out quality over time. So, this base I will cover four different steps in this. One is model generates output, mod output enters data store, data used for retraining, and model degradation accelerates. So basically, I will explain the four steps now. The step one is basically model generates output. Your prediction model is doing its job. It's generating summaries, creating embeddings, labeling data, whatever the task is, right? Now, second is model enters data store. Your generated data gets stored alongside human verified records. Maybe it gets into your data lake. Maybe it is logged for later analysis. Critically, not explicitly tagged as AI generated. There's no provenance metadata saying this output came from model versus this output is human verified. The step 3, use for retraining. 3 months later, you retrain your pipeline. It ingests data from the data lake. It treats everything equally. Your downstream training job is now treating your model output as human labeled ground truth. Now, step 4, model degradation accelerates. What does it mean? It means that the retrained model is now learning from its own mistakes. It amplifies existing biases and errors, and it compounds with each training cycle. Each generation of the model is slightly worse than the last, and degradation accelerates exponentially. This is called model collapse in the research literature, but in prediction or in production, we usually say, why is our model getting worse every time, though we are retraining it regularly? What is the solution of this problem? I would say the solution is basically provenance tagging. We should record each record, and we should have provenance tagging. We should have a specific metadata saying what records comes out of AI model versus what is human ground truth, and they should be marked as such. We should treat synthetic data and human verified data as different classes. We should never mix them, and anytime you are trying to mix them, there should be explicit revalidation. Now let's discuss about why the traditional monitoring dashboard aren't helping to catch AI failures. So this brings us to failure pattern number 5, which is observability gaps and semantic failures. So let's discuss. So basically, let's just think about a scenario. Your pipeline is processing 10,000 requests per second. Your latency is sub 10 milliseconds. CPU and memory utilizations are normal. Error rate is 0%. Your dashboard is completely green. Your on call engineer is sleeping soundly. Now, meanwhile, your model is producing dangerously degraded prediction at scale. It's hallucinating facts. It's showing bias. The confidence scores are dropped by 20%. But none of this is visible to a standard monitoring. And why is it not? Because traditional monitoring or cloud observability stacks are designed for deterministic services. They track latency, they track throughput, they track error rates, resources, resource utilization, operational health, and all of those are important. No one can deny it. But they tell you nothing about the semantic quality of your output. And now let's look at the sheet. Let's look at the comparison. What we can see, on the dashboard we can see request latency, CPU utilization, memory serving error rates, queue depth, infrastructure health, and other parameters that we capture about the pipeline. All reliably instrumented by existing tooling like CloudWatch, Datadog, etc. Right? But what exactly stays hidden? Your prediction drift, your confidence score, your semantic correctness of output, your feature distribution shift, your downstream business impact, everything stays hidden. And this is the gap, right? Your infrastructure looks healthy, your business outcomes are degrading, and you don't even know why. The solution is not about abandoning infrastructure monitoring. It is to extend your observability stack into semantic layer. You need to instrument not just how fast your models are responding, but we also need to understand what exactly are they saying. So let's move on to failure pattern number 6, which is infrastructure level risk. We specifically will cover uh, cost and automation complacency. Okay, now let's talk about what exactly is a non-linear inference cost first, right? Which is on the left side of the sheet that I've shared. In traditional services, cost scales approximately linear to the load, right? You double your traffic, you roughly double your cost. Simple. But AI inferences does not work this way. Costs can scale up unpredictably. But why it happen? Why is it the case? Why can't it basically approximately work like traditional microservices, right? Because input sizes in the AI system dramatically affects the cost. For example, one user sends a short prompt and it will cost like around 1 cent or maybe lesser than that. But another user sends like a 10-pager document, it will cost like half a dollar. It has the same endpoint, the same infrastructure, but 500 times cost difference. So basically, you cannot budget AI system the way you budget your traditional APIs. AI system come in discrete sizes, and sometimes the quality gap is bigger than the cost gap. While traditional system in the traditional system you scale smoothly, you need 20% more power, add 20% more servers, pay 20% more. But in AI, you need to maybe you try a 7 billion parameter model. It's quite good enough, but this is not what you need, right? Then you go into a bigger model. You try 13 billion model. Better, way better, but still not meeting your accuracy threshold. So then you are forced to jump into 70 billion parameter model because that is the next available model in the market, and they hit you target and you actually hit your target quality, and your cost jumped 5x from 13 billion and 10x from 7 billion parameter model. So a 2x improvement in the quality might require 10x increase in the cost. This makes AI system very difficult to budget for and nearly impossible to gap quality trade-offs. Let's talk about the second section of this failure pattern, which is automation complacency. What exactly is that? It is a very important topic that everyone should understand. As the AI system handle more operational decisions, automated retraining triggers, automated data quality gates, automated anomaly resolution, human oversight naturally decreases. And this is rational. Engineers stop reviewing what automation is doing because everything works. We are busy. We trust the system. I myself have done that. If my pipeline is running fine, if I'm not seeing any errors, if everything is looking good, I rarely go and check my pipelines. But this is precisely when the silent failures go unnoticed the longest. Automated pipelines reduce alert fatigue, but they also reduce attentiveness. Edge cases accumulates outside human review window. Failure modes that automation wasn't trained to detect on pass undetected. So what exactly is the lesson we are learning from here? The lesson is automation is powerful, but when unchecked, it is very dangerous. You need to design human in loop checkpoints at strategic points, not not as an afterthought once you start receiving errors or failures. This should be your architectural requirement. So, these are all the failure patterns that I wanted to cover for today. But we have spent a lot of time in discussing about failure modes. Now, let's shift gears and talk about the solutions. So, the good news is these problems are solvable. Whatever six failure patterns we discussed, these are all solvable. And here's the key point: you can't fix a badly designed pipeline by adding safeguard later. You have to build them from day one. This needs to be planned into the system design, not just added with better tooling afterwards. And uh, what I exactly mean is you cannot just add more monitoring dashboard. It won't save your pipeline unless you have metadata tracking, unless you have drift detection, right? But human review gates are very critical. You have to add those in your pipeline. So let's review like the five different steps that I have pointed out in this sheet to look what exactly it looks like in practice. So I have seen this in real production system, and they are not just theoretical. So these are better tested in production to design your pipeline in the most resilient way possible. But here's the mind shift. We need to have some kind of mindset shift, right? In traditional approach, we used to build the pipeline, we deploy it, we wait for something to break, we scramble it and hope it does not break again. But in resilient approach, the one that we are discussing now, we have to design for failure from day one. Assume drift will happen, which is inevitable. It will happen. Assume error will compound, which, as we all are working in data space, we know it is again inevitable. It will come. Build system that catch your problems early and trace them precisely and recover gracefully. This is what we need to work on. We need to work on a resilient approach, which has a shift from the current traditional approach that we are following. So we in the diagram we are describing five different points as I mentioned. So the first one is actually a metadata first architecture. We will cover everything in detail, but as of now I'm just giving like brief idea because we are seeing diagram over here. So first one is metadata first architecture. What it actually means is we have to treat provenance, lineage, confidence as core infrastructure elements, not an optional annotation. Every piece of data should carry metadata about where it came from and how confident we are in it. The second thing is explicit trust boundary. We should explicitly have trust boundary. We should have segregate data between verified zone and unverified zone with hard enforcement that these data should not be merged together and they should live in separate zones. The third is basically human in the loop checkpoints. Strategically placing human review gate at critical decision point to catch what automation misses. This is the most important step, I would say. In my personal experience, human checkpoints are always necessarily, especially in regulated industries like healthcare, finance. So the fourth one is basically semantic observability. So we have to extend our current monitoring stack beyond just regular traditional metrics to cover semantic errors and semantic changes as well. Now, the fifth one is basically uncertainty propagation. So we have to make sure that the confidence score from one model follow through the entire chain and entire pipeline stages. So for example, if a model A is producing 60% confident and model B is the downstream, it needs to know that the upstream only has 16% confidence and it should weigh its input accordingly. So these are the patterns which work together. They reinforce each other, and most importantly, they turn silent failure into visible, debuggable, and recoverable incidents. So let's dive into each one in detail. So the first architectural pattern is metadata first pipeline. So here's the core idea. So we will treat provenance, lineage, and confidence as first class citizens of the data artifacts, not as an optional annotation, as we discussed earlier. What does it mean in practice? So, what exactly it means is for each record leaving or entering the model, it should carry a structured metadata with it. At minimum, it should know where the data come from, what model, the what kind of model version it got produced from, what was the confidence distribution at inference time, and has it been human verified. We should understand the trust level as well. So let's break down the three components what I discussed: provenance, lineage, and confidence, right? As first class individuals. So provenance basically is, we should, for every synthetic data or model generated data, it should marked as such. Like whatever data is human verified, it should be marked as human verified or human generated. Whatever data is coming out of the model, it should be marked as a model generated output. That prevents AI data from silently infiltrating your training data set. Remember the contamination feedback loop we discussed earlier? This particular provenance tagging breaks it. You always know what is human verified versus what is model generated by making sure that provenance tagging exists. Now, the second thing that we like to cover here is lineage graphs. So end-to-end lineage tracking enables engineer to trace any output back through the full chain of model. For example, feature transformation, data sources, everything should be tracked. When something goes wrong at the end of the pipeline, and for sure it will, you can trace it backwards and understand from where it got generated, whether it got generated in stage 1, whether it got generated in stage 2. We should know from where it originated. This makes root cause almost traceable, and even in deeply chain pipeline, you will be able to trace it back to the origin state. Now the third one is basically confidence propagation. So we all, every model generates the confidence score, right? So we should inference the confidence score that are carried forward as metadata in the downstream stages. This is very critical. If the upstream model is only 60% confident, as we discussed, the downstream should know the confidence level, and it should not treat all their inputs equally. It should consider the confidence level as well. So basically, this is a shift in the mindset. Metadata isn't just nice to have, it's the core infrastructure. Let's move ahead to the second architectural pattern, which is explicit trust boundaries and inhuman checkpoints. So let me first cover what is explicit trust boundary, which is on the left side of my uh, presentation. So prediction pipeline must enforce clear demarcation between data zones on verification status. Um, Basically, there are two different verification statuses: a verified zone and a unverified zone. A verified, unverified zone is actually marked as red. Verified zone is actually marked as green here. What exactly is covered in an unverified zone? Any kind of raw model output, any synthetic data, unreviewed inferences. Anything that hasn't been verified by human comes under unverified zone. What comes under verified zone? Human review records, validated ground truth, audited data set, data that you can actually trust comes under verified zone. These should exist in distinct data stores with access control and transformation rules that prevent mixing of these two data between these two zones. Any cross border movement, moving something from verified to unverified or unverified to verified, should explicitly be revalidated by human. And why this is so important? Because it prevents the contamination feedback loop that we discussed earlier, right? It will stop your future, like for the models to keep generating contaminated and garbage predictions. Now let's move on to the second topic, which is inhuman checkpoints. So this is my favorite one. So not every pipeline decision should be fully automated, right? Strategically, we should place a inhuman review gate for this circuit breakers. This will act as a circuit breaker. They catch silent failures even before they propagate further down in down chain pipelines. So for example, for high stake inference path, right, which requires human sign off before acting on outputs. For example, if a model is making a decision which affects human lives, a inhuman checkpoint is absolutely necessary. A human should review it. Now, for example, what exactly is retraining triggers? Retraining triggers are basically something which, for example, if a model is getting retrained on the output of a previous model, before the versions are getting promoted, we should have a inhuman checkpoint. So they everything should be reviewed before new model versions are promoted. Now, Uh, what exactly is data quality gates? Sorry, I missed drift alerts, right? What exactly is drift alerts? Drift alerts are basically the alerts, the drift that we discussed. So when if we have implemented drift, if we are getting drift alerts, we escalate it to human review rather than going through automation checks, right? We
It seems like we lost the speaker. Just bear with us for a second, okay, until she's back. In the meantime, if you have a question, feel free to post that. Things happen, Tim, sometimes.
Sorry, I don't know what happened, Sean, but I was kicked out of the meeting.
Yeah, and I'm not sure. We just lost you, but sometimes that happen. Don't worry about that. Could you please share your screen one more time?
Sure.
Yeah. And also we have two questions. Yes, the sessions will be recording, and it will be available. The second question is, could you please get this presentation? This is very useful. Will you share this presentation?
Sure, yeah, I can.
Okay, perfect, great. And there's another question, say, could you please let us know how much there's implementing this pattern increase latency?
Uh, yes, I will answer that after the end of the session. I just have like few more slides left.
Please
Um,
proceed. Thank you.
can you all see my screen? Uh,
Yes.
okay, so I was basically talking about drift. So once anyone receive drift alerts, it should go for human review rather than automated remediation alone. Then what exactly is data quality gates? It actually includes periodic manual audits beyond automated checks. So basically, if we just remove the above 3 points, with data quality gates, we should always have manual audits by human. So, and honestly, you all will be surprised what with what you actually find. These checkpoints might slow things down slightly, yes, but they actually prevent catastrophic failures in future. So let's move on to architecture pattern number three, semantic observability in AI pipelines. So remember, we discussed about observability gap earlier. This is how you will actually close it. So you extend your monitoring stack beyond infrastructure metrics into the semantic layer by basically instrumenting what your model is saying, not just how they are saying it. Here are the four specific techniques that we should follow. The first is prediction distribution monitoring. The second is feature distribution check. The third is confidence score tracking. And the fourth one is shadow evaluation pipelines. Let's discuss each one in detail. The first is basically prediction distribution monitoring. So we will track the statistical distribution of the model output over time. We will plot histograms, we will track percentile, but if you see any sudden shift in the output distribution, even without your infrastructure alerts, this is an early indicator of upstream data drift or data contamination. So this is very important. It's very easy. For example, if a classification model used to produce like 60% in class A and 40% of class B, and it is suddenly saying 90% class A, there's something wrong. Something has changed for sure. Now, the second one is feature distribution check. Uh, what do we cover here? We regularly compare the live, how your live data looks like against what your training data looked like. Use statistical tests to check if the patterns have changed over time. We should set up automatic alerts if things started looking different. This way, we can catch drift before it actually affects the downstream models. For example, if your model was trained on user session averaging around 5 to 7 minutes daily, but suddenly you are seeing average of 15 to 20 minutes, I think something has changed, something is different, and this is how you detect problems early before they actually cause damage. Now, the third one is confidence score tracking. So as we know that you watch your confidence scores of your model in its predictions. If your model average confidence start dropping, even when the accuracy hasn't changed, this is an early sign. For example, if a model is predicting 80% or 85% of the confidence, but you notice it dropped to 70% past in the last few weeks, something is wrong, right? Now, the last one and not the least, shadow evaluation pipelines. Again, my absolute favorite part. You should run a shadow pipeline that samples live inference output and routes them to periodic human evaluation. And it should basically compare the quality of the output against the agreed quality criteria. Maybe you will just route 1% of your traffic and have domain experts review it. They can check things like, is the output factually correct? Is it coherent? Does it actually answer the question that we are looking for? Are there any hallucination or biases? This provides a good ground truth signal that automated metrics cannot replace. It is expensive, yes, hell yes, but it for high stakes systems like healthcare, and where the lives actually matter, it is worth it. So these four techniques will give you visibility into the semantic health of your AI system. It's and not just operational health. Now let's move ahead into uh, the tooling ecosystem. So the good part is, mm, you do not have to build everything from scratch. There are mature tool available on in market, and you can use them for your data quality and drift detection. There are a bunch of tools. Great expectation for data validation, Evidently AI for drift detection and monitoring, logs for data logging and profiling. And these above three tools will help you catch data quality issues and distribution shift before they propagate. The second is for pipeline lineage and orchestration, Airflow for workflow orchestration. This is what I use on day-to-day life. This is my go-to thing. It's very easy, super easy, and super visually understandable. and prefect for modern data pipelines, and DBT for transformation lineage. The above three will give you end-to-end lineage tracking that we talked about. The third one is model monitoring and observability. Azure AI for model performance and monitoring, Fiddler for explainability and monitoring, and weights and biases for experiment tracking and monitoring. These will extend your observability stack into semantic layer. And for human in loop fireworks, Label Studio, Prodigy, Snorkel can be used, and these are very practical to implement the human in loop checkpoints that we discussed. Again, I'm not endorsing any brand here. I just evaluate what works best for you. I have used some of them, not all of them, so I cannot count for all, but the whole point is the ecosystem exists. You don't have to build everything custom. So let's just move into the final uh, sections of this presentation, the key takeaways. So we have covered a lot of ground truth, right? Let me bring this together into four key takeaways that you can bring back to your team. So the takeaway number one is basically silent failures are design problem, not monitoring problem. What does it mean? It means you cannot just fix things by adding more metrics into the dashboard. Traditional monitoring are designed for operational metrics and to fail in a predictable ways. Either they work or they crash. But in AI system, things fail gradually. They keep running while quality degrades. So you need a completely different monitoring approach for this. One that tracks the semantics, uh, uh, one that tracks what your model is saying, not just how fast they are saying it. And that is not something that you bolt on later. It has to be built in your system design from day one. Now, what is the takeaway number two? Treat every AI output as probabilistic, not authoritative. So never let your downstream pipeline assume that its input are ground truth without validation or verification. Design downstream customers to be aware of upstream uncertainty. Propagate confidence metadata. Build trust boundaries. This is a shift in mindset and that prevents error compounding. Now, takeaway number three is basically provenance and trust boundaries are non negotiable. This is very important. AI generated data contamination happens because of no provenance tagging and no trust boundaries. And that causes a lot of failures in production ML system. It is dangerous because of the feedback loop. It will keep getting worse over again and again. You have to tag everything, segregate trust levels, audit the boundary regularly. This is not optional, this is mandatory for AI pipelines. Now, the takeaway number four, automation complacency is a systematic risk. And this is the one I want you to leave with. Understand this, the most reliable your automation becomes, the more dangerous unchecked automation becomes, right? This sounds paradoxical, but it is true. When automation works 99% of the time, human stops checking, and it happens, it's human behavior. And this is when 1% of the edge cases slip through unnoticed for weeks and months. So in human loop checkpoints becomes mandatory here, and they are the decision points, they are not the afterthought. They should be your architecture requirement. These are the principle, and we should make them concrete. So here's what you should start this week if you are designing a pipeline. If not this week, you can take this with you and design whenever you are working on an ML pipeline. I don't want you to leave thinking that, okay, that was interesting, and then going back at your desk, you are doing nothing. So I've put together like a practical checklist of five things you can start with. First is action one, which is audit metadata. Absolutely, absolutely necessary. Review your pipelines for missing confidence and provenance metadata. Pick your highest traffic pipeline. Trace one output backwards and try to answer these questions. Can you determine its full lineage? What model produced it? What is the confidence score? If you cannot answer even one of these questions, you have a metadata gap. So start instrumenting. Action number two, implement drift detection. pick your highest traffic model and implement at least one basic drift check. You can start simple. You can monitor distribution of your top 5 features and compare them against the prediction model, or compare them against training. Set up an alert. You don't need to use a fancy tool. You can just use your basic statistics. You can use Excel and but have a cron job on top of it so that it runs regularly, and start measuring, start alerting for data drifts. Third is, again, one of the most important ones, segregate data. Separate AI generated data from human verified ground truth in your data scores. If they are mixed right now, and I bet they are right now, create a separate table and separate buckets for them. Enforce clear trust boundaries between verified versus non verified data. Now, action item number 4, add semantic metrics. Add at least one semantic quality metrics to your monitoring dashboard, not latency, not throughput, something that measures what your model is saying. Average confidence score works, output distribution percentile works, anything works. Just pick one and just start with it. Now, action number 5 is add a human review gate. Again, absolutely necessary, but you can identify one high stake model and decision point in your pipeline and integrate a human review gate. Maybe it's before training, maybe it's for high value prediction, maybe it's for edge cases, but start somewhere. You can always optimize later. So you all start with one of the actions, start with more, but you should pick one and start. And this brings us to an end. Thank you all for your time and attention today. I hope this session has been useful. Uh, but to recap overall, I would say silent failures in AI systems are real, they are pervasive, and but they are solvable. But only if you change how you design and operate these systems. These patterns we discussed today, metadata first design, trust boundaries, human in the loop checkpoints, semantic observability, these aren't theoretical, these are better tested in production. I will love to hear about your experiences if you have encountered any of those failures in your own systems, or if you have implemented something that can benefit each one of us. I'm always interested in learning. I can take a question and answer now. And if we are short in time, like later, I have also created like a Google Sheet which I can post. It is available for 4 hour post session. You can post your questions and I can get back to you uh, on this like as soon as possible.
Outstanding. Thank you so much for putting this together. That was amazing. Team, you all have access to unmute yourself. What I would suggest you to do is if you have a question, please raise your hand first. Let's do it in sequence order and then come off mute and ask the question. Thank you.
Should I start with answering the questions that those are in the chat? Okay. So
I
thank you,
think,
Durga. Mhm.
sorry about that. I think we have Rupal. The virtual hand is on. Do you mind to go from here instead? Pick
Yes.
Rupa. Mm-hmm.
Hi, Rupal.
Hello. Thank you for such a great session. Very informative. So we talked about training data. We know how important our training data is for our accurate model. So I was wondering, how do we make sure that our training data is not contaminated by AI generated outputs?
I would say, Rupal, if you are asking this question, for sure your data is contaminated as of now. If you are not doing segregation as of now, that is where you should start with. You should start seeing if you have tagging in in your data set, or if you have like explicit human marked verified boundaries. If not, then start tagging data right now. Start looking in in your bucket, see if you have correct metadata or not, and then start from there. But as of now, if you are asking this question, I'm sure it's still, if your model must be using AI generated data. And
Perfect.
I would say first stop the bleeding, clean up the space, and then retrain
Yes.
your model.
No, that makes sense. You're right. Thank you.
Yeah.
Yeah, feel free to go over the question on the chat.
Okay, so the first question is asked by a guest, Durvadas. They have asked how much does implementing these patterns increase latency? I would say the latency effect is minimal. Um if you are implementing drift, it happens asynchronously at the background. If you are talking about adding confidence scores, they are already there in the model. You just have to propagate to the downstream layer, so the latency effect is minimal. If you are talking about metadata tagging, you just have to add few more columns, so very negligible. The only place where your latency would impact is in human checkpoints, but honestly, those are very important. You can decide and strategically place inhuman checkpoints to your high stake model where it is impacting customers. So overall, 90 to 90% of 5% of the pipelines, it might latency might be negligible. Only that human inhuman checkpoints is where it can impact. Let me go through the second question. Um, it's from Anurag Mishra. The key difference between data and concept drift. I would say data drift is saying what basically what we are seeing versus concept drift is what exactly it means. So I would say data drift is when your input feature distribution change. For example, if your user suddenly start behaving differently than they did during training, so that means we have a data drift. But when you say about concept drift, it means the relationship between your input and outputs change. The example that I took initially, right? When we were saying that the UI has been redesigned, now the click on the convert button is not actually conversion. It means the users are more, uh, they want to just learn. They don't want to just compare. They are more curious. So that means the relationship between your input to output change, that is basically a concept drift. Thank you, Gitansh. And Anubhav asked, what is the ROI on inhuman loop checkpoints? This is a very interesting question for ROI. Uh, so usually for ROI, I would say if we compare the ROI of getting errors and then resolving it overnight, it is less. So for example, if we are investing a 30 minutes to 2 hours for each um, employee every day to do a inhuman checkpoints, it is high, but it would be considerably low if your model fails and you have to do a like an overnight debugging. So what we actually how we actually calculate this is how much are you paying to recover from that one time of like over basically one time of failure and over months of bad prediction to investing 2 hours or 30 minutes of inhuman checkpoints every day. So the ROI, if we compare like that, is less, but overall the ROI for inhuman checkpoints will be high. I think Pitambra asked how often should we check for drift. I would say that depends upon your use case. The first one, for example, if you are in a highly changing industry like social media or the let's just take an example of social media. I'm just getting that on top of my head. If you are in a highly changing industry like that, you should check for drift regularly, like maybe in a once a day or twice a day, because user interest changes frequently. But if you are in a stable and a regulated industry like healthcare, finance, where things does not change very often, or medical industry, right, pharmaceutical, you can change like check for drift once a month. So it depends upon your use case completely. Toby asked, how do we monitor drift or segregate model generated data against verified data for pipelines where AI external model could happen uh, further upstream? So, Toby, as I have mentioned in my slides, we should monitor for drift separately. it the drift will reduce. It is inevitable. Drift will always be there because the user preferences will change, user criterias will change, like the surroundings will change, right? As I took an example of shopping between January to March versus shopping in holiday time period, right? So drift is inevitable. So you have to keep monitoring. You start slow, you just start monitoring drift in a regular Excel sheet if you have a single AI model. But to segregate your data, you have to you have to keep your AI generated data, which is a verified which is a non verified data, and your verified data in a separate bucket altogether. Anytime you want to use your AI generated model output, you should explicitly revalidate it with user. I hope that answers your question. Uh, yeah, I think we are good. Sean, I think those are all the questions we had. I have also pasted my Google Sheet. It's editable for next 4 hours. If someone wants to just post their question post this session, I will be happy to answer that.
Also, can you share the documentation for the presentation? They can
Sure,
download it as well. Mhm.
sure. Yeah.
Um,
So
uh,
should I share it here?
yes, so therefore everyone can have
Yeah.
access to it. Mhm. Perfect. I think Koshi had a question. It seems like you just lower your hand. Was that a question, Koshi?
Yes, I
KHUS
was just gonna ask a last question if that's okay.
Akanksha?
Yeah, yeah. Yeah, go ahead,
Mhm.
please.
I was just gonna say, what if we are already training on AI generated data? How do we fix it?
So honestly, if you are already training on AI generated data, your model is already training on bad records. What you have to do is you have to start adding metadata to your AI generated output, and try to add metadata to the already existing outputs. If you cannot segregate those, unfortunately, the only solution over here is you have to retrain your model on the original training data set and start from scratch, because your
Okay,
model is
thank you.
continuously producing bad results all the time.
Yeah.
Um, Let me get the document here.
I can see a lot of thank you. Akanksha, you did an outstanding job.
Thank you so much.
So we hope to have you next year again if you have time on your calendar for that.
Definitely. I would love to do that.
Oh, thank you.
So let me
Tim,
find
I
the.
think it's all set. Um, you are free, for example, to post that after. It
Mhm.
doesn't have to be right now, so therefore we can release everyone on the call. If there are no more questions, let us, if you still have questions, let us know. Otherwise, we would like to end the webinar. And sorry, I didn't see the link. Toby, she's about to do that. It seems like she might need more time,
I
especially
have, sorry, Sean. I have the presentation, but I have, this is my first time using Teams. As you see, multiple times I have faced issues. So how to exactly upload it?
oh no, that's fine. This is what we're going to do. Share it with me on LinkedIn and I will upload it here
Okay,
after for everyone
okay,
to access it. Yeah.
perfect.
So
Yeah,
thank you. Thank you one more time, Akensha, and thank you everyone. If you haven't registered yet, we have a tons of presentation lined up for you and we meet every Thursday at 12 p.m. And our community mainly focus on data, AI and visualization. Enjoy the rest of your day. If you're already on Friday, enjoy your weekend and see you next week. Thank you again. Bye bye.
Thank you so much. Bye bye, everyone. Thanks for joining.